Welcome, architects, to an essential deep dive into navigating model interaction workspaces. Today, we are laser-focused on adjusting temperature and randomness controls. Welcome back to the lab, architects. Today, we are diving deep into the interaction workspaces of Amazon Bedrock to master randomness controls. To truly master generative artificial intelligence, we must first understand how large language models construct their responses. What does that mean in practice? When you submit a prompt, the model does not just magically understand sentences. Instead, it breaks your text down into tokens and calculates a massive probability distribution to predict the single most likely token to follow. It analyzes its entire pre-trained neural network, scoring thousands of potential words based on their mathematical likelihood. By default, a model will always want to pick the token with the highest probability. But if it always picked the most likely word, the outputs would be incredibly robotic, repetitive, and frankly, quite boring. This is exactly why we need inference parameters like temperature, top P, and top K. These controls allow us to shape that probability distribution dynamically. It is fascinating to think about. Imagine asking an LLM to complete the sentence, "Kids love to eat." The model might generate a distribution like pizza at 50%, vegetables at 30%, and ice cream at 20%. How the model samples from that precise distribution is entirely dictated by the randomness controls we define in our API payload. Mastering this unlocks the true power of prompt engineering. Let us get hands-on and tame the math to build incredible applications. This flowchart reveals the invisible cognitive process. Our prompt input is tokenized, driving a massive probability distribution calculation. Then, our crucial randomness controls mathematically filter the options before making the final token selection. Let us dive into our first and most famous style, temperature. How exactly does temperature impact our generative models? Mathematically speaking, temperature is an element applied to the probability mass function for the next token. It determines how much randomness is injected into the generated text. Serious, temperature typically scales from 0 to 1, though some models permit slightly higher values. When you configure a low temperature, near 0, the function's steepness increases dramatically. This forces the model to ruthlessly favor the absolute highest probability tokens every single time. The result is highly deterministic, predictable, and conservative output. This is perfect for analytical tasks, code generation, or extracting data where facts matter more than flair. But what if we crank the temperature up to 0.9? Excitedly, the probability distribution magically flattens out. Returning to our kids love to eat example, pizza might drop to 30%, while ice cream rises to almost match it. The model starts taking creative risks. It selects less probable outputs, leading to highly diverse, innovative, and human-sounding text. However, you must be careful. If you set the temperature too high, the model might select completely improbable tokens, causing the text to degrade into bizarre, hallucinatory gibberish. The art of generative AI architecture is finding the exact optimal temperature for your specific use case. A legal contract requires a low temperature, while a marketing slogan thrives on a high temperature. Observe the temperature spectrum. Low values drive strict, deterministic, and factual responses. Medium provides balance, while high values unlock extreme creativity and diversity, albeit with a slightly higher risk of hallucination.
Understanding theory is great, but as architects, we need to know how to implement this in code. When we interact with Amazon Bedrock via the AWS SDK for Python, known as Bodo3, we pass these randomness controls directly inside our JSON payload. Let us look at exactly how we inject temperature into an inference request for the Amazon Titan Text Foundation model. We must define a specific dictionary block, often called text generation config, or simply map it into the base parameters, depending on the specific model's required schema. Because Bedrock provides a unified API, the wrapper remains the same, but the internal payload must match the provider's expectations. Long pause. Let us examine a highly optimized block of Python code that programmatically turns the creative dial up to 0.8 for a brainstorming task. Let's break down this programmatic masterpiece. We instantiate our standard Bodo3 client targeting the Bedrock one-time endpoint. The magic happens inside our payload JSON object. We supply our input text asking for unique sci-fi game names. Then we explicitly declare the text generation config dictionary. Inside, we set the temperature to 0.8. Because we want creative, non-obvious game names, this high temperature forces the Amazon Titan model to sample from a much flatter probability curve. We then invoke the model, passing our payload and the amazon.titan.tg1-large model identifier. Bedrock securely processes the mathematical sampling on its massive GPU clusters and streams the JSON back to us. By simply changing that single decimal value in Python, we completely alter the cognitive behavior of a multi-billion parameter neural network. This logic traces our Python execution. The Bodo3 client packages the high-temperature JSON payload, transmits it via the invoke modal API, forcing Titan to evaluate a flatter mathematical curve to return highly creative text.
While temperature flattens the curve, it does not mathematically eliminate the worst options. That is where our next control comes into play. Top P, also known as nucleus sampling. Top P operates on a completely different mathematical principle. Instead of adjusting the likelihood of all tokens, Top P restricts the model's choices by establishing a hard cumulative probability threshold. How does this mechanism work? Imagine the model calculates the probabilities for every single word in the English language to follow your prompt. If you set top P to 0.9, the model will rank all words from most likely to least likely, and then add their probabilities together until they hit 90%. Any word that falls into that bottom 10% of the long tail is ruthlessly chopped off and discarded. The model is dynamically resizing its vocabulary pool at every single step. If the next word is highly predictable, the nucleus might only contain 2 words. If the next word is ambiguous, the nucleus might expand to contain 50 words. By utilizing top P, we ensure that the model can be highly creative, but we mathematically guarantee that it will never select absolute gibberish. It is the ultimate safety net for generative AI creativity. Observe the dynamic nucleus logic. Tokens are ranked, and their probabilities are summed. If the sum is beneath the top P threshold, they enter the pool. Once the threshold is breached, the rest are instantly discarded. Having mastered temperature and top P, we must introduce the final pillar of randomness controls, top K. While top P is dynamic and based on percentages, top K is an absolute, rigid numerical boundary. When you configure top K, you instruct the foundation model to sort the possible next tokens by probability and then literally discard everything beyond the kth token. For example, if you set top K to 50, the model will only ever look at the 50 most likely words for the next step, completely ignoring words ranked 51 through 50,000. It is a blunt instrument, but it is incredibly effective. Why would we use this? Sometimes, even with top P enabled, a very flat temperature curve can still allow strange, unnatural words to creep into the nucleus pool if the overall distribution is extremely uncertain. By enforcing a top K cutoff of 250, you mathematically guarantee that the model will never randomly select a bizarre, archaic word that ruins the coherence of your application's output. Excitedly, while some newer models actually disable top K by default to rely purely on top P, many foundation models on Amazon Bedrock still fully support top K sampling to give you absolute, granular control over vocabulary boundaries. This flowchart demonstrates the brutal efficiency of top K. The sorted list hits the strict boundary filter. Exactly K tokens are retained for sampling, and the entire remainder of the vocabulary is completely deleted from consideration.
Now for the masterclass. How do these three parameters interact when deployed simultaneously? You rarely use just one parameter in isolation. In Amazon Bedrock, orchestrating temperature, top P, and top K together creates a highly sophisticated cognitive filter. Let us trace the execution sequence. First, the top K parameter applies a hard cutoff, severely restricting the overall vocabulary to a fixed number. Next, the top P parameter dynamically analyzes that remaining pool, trimming the long tail of probabilities to ensure only the highest quality tokens remain. Finally, the temperature parameter scales the mathematical weights of that highly refined filtered pool to determine the ultimate randomness of the final selection. It is a three-stage mathematical gauntlet. However, a critical best practice is to avoid conflicting adjustments. If you lower the temperature to 0.1, the model is already purely deterministic. Adjusting top P or top K will have absolutely zero visible effect because the model is only looking at the number 1 token anyway. Conversely, if you crank the temperature to 1.0 for maximum creativity, you absolutely must engage top P and top K to prevent the model from hallucinating. Mastering the interplay of these parameters is what separates amateur prompt engineers from enterprise-grade generative AI architects. Watch the three-stage gauntlet. Raw data hits the strict top K cutoff. Then the dynamic top P nucleus filter refines it. And finally, temperature scaling adjusts the distribution before producing the optimized output. As we wrap up this module on randomness controls, we must discuss enterprise best practices and the financial implications of your configurations. Every foundation model on Amazon Bedrock, whether it is Anthropic Claude, Meta Llama, or Amazon Titan, has a slightly different baseline behavior. A temperature of 0.7 on one model might act like a 0.9 on another. How do you mitigate this? You must utilize the Amazon Bedrock Chat Playground's compare mode. This invaluable feature allows you to execute the exact same prompt with different parameter configurations across multiple models side by side. It provides immediate visual feedback on how your dials are impacting coherence and creativity. Furthermore, bad parameter tuning has a direct impact on your AWS billing. If your temperature is too high and your top P is unrestrained, the model might ramble incoherently, generating hundreds of useless output tokens. Because you are billed per output token, poorly configured randomness directly burns through your cloud budget. Excitedly, by strictly tuning these parameters, you guarantee concise, high-quality, and cost-effective operations. I hope this technical deep dive has empowered your architectural skills. We invite you to like, subscribe, and visit quicktechie.com for premium and for recently updated material as per latest syllabus and certification prep, including Q&A banks, ebooks, audiobooks, full training, and interview guides. The enterprise lifecycle dictates that parameter design must be rigorously tested in compare mode. We then analyze the exact token output costs before deploying a strictly cost-optimized configuration into our production environment.